So this video we're going to talk about convergence of a discrete time Fourier transform. If you recall from the last section, these are the equations we derived. The first equation is called the analysis equation, and we find that it summation from minus infinity to infinity, and as soon as you see a summation from minus infinity to infinity, that should raise a question in your mind that there might be a conversion issue that's going on with here. So that's a bit of a problem. But as far as this one is concerned, as you can notice, is over a defined period of 2 pi, so it has no conversion issue. Okay, it basically, actually, better way to say that is always converges. So we don't have to worry about that. So when we are trying to take a Fourier transform of a signal, we really should be worrying about whether we have that convergence or not. And in order to make sure that we are in good shape and the signal can be can have a convergence, we need to make sure that the summation from n going from minus infinity to infinity of magnitude of x of n e to the minus j, I'm sorry, no, there's no that. We just got to make sure this magnitude, we don't have to worry about e to the j omega n because magnitude of that is 1, we're taking care of. We just got to make sure the magnitude of this is less than infinite. Another way to think about this is that we need the energy, which is the energy would be the square of this, has to be less than 1. So let's look at this thing and say, okay, is this thing absolutely summable? In other words, is it less than infinity? If it is, if true, converges. So we can go on and take a Fourier transform. If not, doesn't converge, which means we have to do other things, which will later on in the Z transform and all that we talk about it. So if not, or if it does not satisfy this condition, then does not converge, which means it does not have a Fourier transform. This, if it's true, if this condition is true, then it converges and has a Fourier transform. Okay, so that's all we have to do to make sure that we have a convergent signal and everything is good. And the Gibbs phenomena that we talked about earlier during the continuous time is still true. The Gibbs phenomena said that as the period increases, the ripples in the partial sum become compressed toward the discontinuity. So another way of saying it is as the middle becomes flattened and the edges where the change in value is happening, it becomes more spiky. Okay, so that's that. And then just as a quick reminder, we do not have to worry about the convergence of the inverse of this because that is has a defined period of 2 pi. And that takes care of discussions around discrete time Fourier transform convergence.